Alrighty, so we have here a data set where I have mapped out a participant's average free time per weekday, average throughout the week. Oh, for heaven's sakes. Their hours of sleep per night, average throughout the week, and their hours of exercise per week. And we're going to say we've given them a happiness scale that you can score 1 to 20 on. And this is what we're going to use for our regression. I am providing an annotated output for you, so don't feel like you have to furiously write down every single thing I'm saying about the output, because I am going to provide an annotated version for you that is already posted. So you might want to pause me, download that, print it off, pull it up next to the screen, whatever, so you can follow along. But let's go here. We're going to click on Analyze. We are going to click on Regression, and we're going to click on Linear. Logistic regression is a really interesting variation where you can actually predict what group someone is going to belong to. Totally separate topic, but that's, if you're wondering what that option is, that's what that is. So we're going to go to linear regression. Now, what you're going to see, I should have cleared this out, is a starting list that looks like pretty much every starting list we've had so far in using PSPP with our ANOVAs and with our t-tests. So our dependent variable, again, remember what is affecting what? We want to know the happiness scale score. We want to know the way the other variables affect the happiness scale score. So happiness on a scale of 20. For our independent variable or our predictor variables, we want to know the hours of sleep per night, the hours of exercise per week, and the hours of free time per day. Okay, because remember what we're wanting to say is how do these three variables combine to impact this variable? Can I predict a person's happiness score if I know these three pieces of information about them? Let's come over here to statistics. We're going to ask for the coefficient. Let's do it without the confidence interval first. We're going to ask for the R, and we're going to ask for the ANOVA. These two have some really interesting applications, but again, it's beyond the scope of what we're doing here. Maybe sometime we'll teach an advanced statistics class, who knows. All right, let's click continue. So that's all we need for this. Let's click OK. So what you're going to see here is three different sets of information, and you need all three of them. Let's start with this up here. First of all, our R. What our R tells us is the correlation between the observed and the predicted values of the dependent variable based on our regression line. Remember, at the very beginning of this unit, I drew the thing with the y-hats. We were talking about caffeine intake and anxiety, and I said one of the assessments that we're going to make is how do that actual reported values that I have in my data set, how far away are they from what my predictions would have been? That's what this first box right here, this first R is talking about, is what are the correlations between my predicted values and the values that I actually saw. This is pretty strong. This is saying 0.96. There is a 0.96 correlation between observed and predicted. And if you remember our correlation discussion before, 0.96 is a pretty dang strong correlation, right? You're going to have a hard time arguing that that's not meaningful. Now, your R squared is divided into two different numbers. There's an R squared and there's an adjusted R squared. Now, as a whole, what the R squared is referring to, like we already talked about on the last video, is the amount of variance in the dependent variable that is being predicted by our indicator variables. Okay? So what we would be saying here, if we're going to put this into real world everyday language, is 92% of the variance in this sample's 20-point happiness scale score is being predicted from our combination of sleep, exercise, and free time. Now, one thing to keep in mind, this is an overall assessment of this model as a whole. So far, we do not know anything about any one of our individual variables. We can't say which one's stronger, which one has a bigger effect, if any of them are overshadowing the others. Like, we can't say squat about individual variables at this point. All we can say is the three that we proposed are working together. It appears that they are working together and that we're able to predict 92% of the variance when we look at all three of them together. The adjusted R-square considers the number of participants that you have and the number of variables that you are using to attempt to make your R-square as accurate as possible. So what it's doing is it's saying we have to acknowledge, kind of like what we did with ANOVAs, we have to acknowledge that some of this variance is based on chance or coincidence, right? And so if we're acknowledging that some of this is based on chance or coincidence, the more predictions we're trying to make, the more participants we have, the more likely it is that we're going to have some noise in there. And so the software is using a combination of information about the number of predictor variables and the number of participants to adjust this R-square. Sometimes it will raise it, sometimes it will lower it. Again, understanding the math behind that is beyond the scope of what we're doing. A lot of times in articles, both the R-square and the adjusted R-square will be reported. It depends on a variety of factors about how you're going to do that or not. And also if there's a huge difference between them. Now, the standard error of the estimate. Remember we talked about we were going to assess if we have our regression line and we have our actual data points falling over here kind of around these predictions. We need to assess how much gaps there are, right? We already know how much they're correlated based on our R, but we also need to discuss how big are these errors that we have here. And that's what this standard error of the estimate is doing. Is it saying how well our data actually fits to the regression line? A smaller value is going to indicate a better fit. It's going to indicate dots that are closer to the line. So the way we would word this, how we would interpret this, is that we would say the average observed data point in this data set falls 1.46 units away from its predicted score on the regression line. Now, there's a lot of relativity involved in terms of what is small and what is big in terms of evaluating this. If we think about this in logical terms, we know we're dealing with a happiness score that's on a scale of 1 to 20, all right? So saying our average observation on that scale of 1 to 20 is about 1.5 points off from what it would be predicted to be. That's still pretty impactful, right? Like that's saying, if I know your average hours of sleep, your average of exercise, and your amount of free time, I can predict your level of happiness or your happiness score on a scale of 1 to 20 with only about a 1.5 point margin of error. So that's pretty good, right? If we're dealing with a 20-point scale and this was 10, this probably would not be statistically significant. So the smaller this is, the better your fit is. And again, small versus large is going to depend a lot on what your units of measurement is, what the size of your scale is, things of that nature. All right, now the next box we're going to move on to. We're going to discuss the ANOVA output. So the ANOVA happiness scale, the ANOVA of the happiness scale score of 1 to 20. This is going to work differently than the ANOVAs that we talked about a few chapters ago. What this ANOVA is doing is it is answering the question, do the combination of predictor variables that I have included in this analysis accurately predict the expected values of my dependent variable. Are these variables together an accurate prediction? All right, so this is a very different way to apply ANOVA than what we did a few chapters ago. So this ANOVA is looking at, do I have an accurate prediction here? A statistically significant result means yes. A not statistically significant result means no. So since this is statistically significant, what we could say here is the combination of hours of free time per day, hours of sleep per night, and hours of exercise per week can reliably predict a person's score on a 20-point happiness scale. We are answering our question, can I accurately predict it? Yes, I can. Okay. If it was statistically significant, we would say no. We don't have a good combination of predictors happening here. We can't predict the scale. Now again, notice I'm still talking about all three together. If I were to stop here, I mean, it's interesting, but I don't know what part each variable is playing. Okay. And that's where this last box comes in, the coefficients. Now, we need to look at all of these columns. So what this is telling us is where our constant falls. The constant it is rarely of any interest whether or not this is statistically significant. There's a few cases where we could discuss it, but as a whole, whether or not this is a significant outcome, or really whether or not what the value of it is, for the purposes of the very introductory level of regression that we're doing here, don't worry about this one. All you know is this is what gives you your A. When we draw the graph, we pointed where the A would be, where the intercept would be. This is what gives you your A, okay? The constant. Now, so what this table is doing is it's walking through it. Remember, I told you your table is going to give you your unstandardized and your standardized coefficients. If you have no idea what those words mean, please go back and rewatch the last video. So what this is going to do is give you your unstandardized coefficient for each variable. It's going to give you your standardized coefficient, or your beta, for each variable. And it's going to give you your statistical significance for each variable. So the way you read this chart is to go across. So what we would see, hours of sleep per night, has a B, an unstandardized coefficient of 1. Remember, what that means is how much are you going to increase your prediction for every 1 unit that you increase on your X. So what this is saying, this value of 1 means for every extra point I have on hours of sleep, I'm going to see an extra point on the happiness score. Let's go down to the next one. Hours of exercise per week. For every extra point I have on hours of exercise a week, so going from 2 hours of exercise to 3 hours of exercise, I'm going to see a 3-point increase on happiness score. That is pretty significant. We'll see if it actually is, but just looking at that, that seems like a pretty significant hop there. And then hours of free time, for every hour, or for every point I increase on hours of free time, I have just, if I rounded it up, it'd be a 0.5 point, but I have just under a 0.5 point increase on my happiness scale score. So that's how you read these betas, or these, not betas, these unstandardized coefficient, these B's. Now, your standard error here is your standard error of each independent variable. This is telling you how much precision you have in your estimations. A smaller standard error equals a greater precision of your estimate. And you can compare these. So you can see hours of sleep has a slightly stronger fit, a slightly closer fit, a slightly less error than hours of exercise. So these dots, these true data points, are falling closer to our predicted or our expected ones than these. And then you can see there's quite a bit bigger of a hop between hours of exercise per week and free time per day when you compare it to the jump here. Okay, so this can tell you which of my variables is having the most accurate prediction, which one is most strongly fitting to my line of my expected score. And then you have your standardized coefficients. These are the betas. These are the ones that you would have converted to your z-score first. Now, on your betas, the larger your number, the more likely you are looking at a statistically significant result. Because remember, this is converted to z-scores. So the bigger this is, the more likely your result is statistically significant. So we could already look at these. Like if I totally covered up this side of the graph right here, we can look at these and we can say, all right, I have 0.24 and 0.69, and then this little guy's floating down here with 0.07, so he might end up being a problem. So now let's go over to our statistical significance. Hours of sleep per night, 0.042. We made our statistically significant cutoff. This is acting as a significant predictor. Hours of exercise per week, 0.000, right? This is, even if we extended it out to the 0.001 level of statistical significance, this still makes it, right? This is a significant predictor. But notice what happened over here with hours of free time per weekday. This is not significant. And so this is one of the places where we could do a follow-up test and say, all right, that is really interesting. Would it have been significant if we weren't also considering exercise and sleep? Actually, before we get there, one thing to know. If you ever run something like this and you do not have a statistically significant model, like if this was up here, if it was close, if this was up here like 0.06, and you have a non-significant predictor in your results, always try getting rid of your non-significant predictor and see if that will give you a statistically significant model. And that is not a dishonest use of your data. That is not data mining. That is saying, I ran my analysis. This variable was not a significant predictor. When I removed this variable, my model was then statistically significant, if that's the result you get. And then, of course, you'll want to explain, why that might have been the case and all that. So you create a little more work for yourself if you've already laid out a theory of here's why I think all three of these will be significant. But you can look at this and say, okay, my model's not fitting. I have some variables I thought would work and they don't. Let me get rid of them and then see if my model fits. We do it all the time. But let's see if we were considering exercise by itself, what would happen? So let's go back to analyze, regression, linear, and let's get rid of exercise and let's get rid of sleep and let's just look at free time. And let's say, okay. I hate that this doesn't automatically pop up. All right. So now look what's happening. When I'm considering free time by itself without the other two, free time is still up here at a 0.74. So again, what does that mean? I have a 0.74 correlation between my observed and my predicted, with this being the only variable in play. So that's still pretty good. My R-square is 0.55. So I'm predicting about 55% of the variance in happiness. That's still pretty good. I have a significant model. And now hours of free time per week is highly statistically significant. I'm not even anywhere close to saying, oh, this is a fluke result, right? And my B is 4.8. So for every increase in an hour of free time per week, I'm seeing a jump of getting close to 5 points on my happiness scale, right? That's huge. If somebody told you, you could increase your happiness rating on a scale of 1 to 20 by 5 if you can find an extra hour of free time in your day. I mean, that would be pretty impactful. If you were struggling with life satisfaction and happiness, this seems like a hugely significant outcome. But then watch what happens. So we know that that's there. Now watch what happens here. And I actually didn't even do this on purpose. This was just a happy accident when I went through and put in numbers. Let's say I consider free time and sleep together. Okay, I consider free time and sleep together. I hop down here. Suddenly sleep is significant. Free time is not. It knocked it out. Let's see what happens if because I've already considered all three together. I already know what that answer is. Let's see what happens if I consider free time and exercise together. Free time, exercise, again, it knocks it out. The exercise is significant, but the free time isn't. What does this tell me is happening? Let's put this into words. Because again, that's the fun part of statistics. I know that fun might not be a word that you use to describe this class, but that is the fun part of statistics, is saying I have these numbers. What can this tell me about people? Like, what real words can I use to describe this? So how can we put this into real words and real things that can actually help? Okay. So free time, when considered alone, has a drastic impact on your happiness scale. But if I also consider sleep, remember we talked about the shared explanation, right? Actually, let me draw it. That might be easier. Okay. If you followed along on this, you might want to print or save or in some way have this where you can look at it. If you haven't yet downloaded the data set and you weren't working on, maybe like screenshot this where you can have it pulled up so that you can follow along, and I'll have it pulled up on one of my screens, and I'll get the board back on full screen, and we're going to actually talk through the real world results of what we can see happening here. So I will stop this video, and video 4 will pick up with like our real world interpretation of this output.